It is our largest collider in the world.
A new chapter, Run 3 of the Large Hadron Collider, will give us collisions.
The LHC, like all physics experiments, aims to verify theoretical predictions, in this case the so-called standard model of particle physics, and see if there are any holes in them. As strange as it may sound, physicists are itching to find a few holes in the standard model, because there are some things, such as dark matter and dark energy, that can't be explained until they do. So physicists all around the world were ecstatic to see the world's most advanced high-energy particle collider get operational. After all, they had waited decades for this magnificent technology to alter our understanding and understanding of the universe. The Large Hadron Collider has helped scientists solve many of the universe's riddles in numerous runs since its inception. However, only recently scientists from CERN made an announcement that when they powered up the Large Hadron Collider with the new maximum beam of energy, they discovered something unexpected and disturbing. They've been attempting to figure out what triggered this incident since it happened. In today's video, we are going to find out what actually happened. The LHC is a particle accelerator, a device that boosts subatomic particles to enormous energies in a controlled way, so that scientists can study the resulting interactions. These colliders are difficult to build, but they are extremely strong research instruments in particle physics because they attain a far higher center of mass energy than fixed target configurations. Scientists can then examine the results of these encounters to get insight into the structure of the subatomic world and the fundamental principles that govern it. Many of the byproducts are only formed by high-energy collisions and decay in extremely short periods of time, making it impossible to examine them in any other way. The Large Hadron Collider is housed in a circular tunnel that is 50 to 175 meters underground. This depth variation was intended to limit the amount of tunnel that sits beneath the Jura Mountains in order to prevent the requirements for the excavation of a vertical access shaft there. This tunnel was chosen so that CERN would not have to spend the large sums of money on expensive surrounding land. The protection from background radiation provided by the Earth's crust was an added benefit. The 3.8-meter wide concrete-lined tunnel was built between 1983 and 1988. Previously, it housed the massive electron-positron collider. This tunnel crosses the border between Switzerland and France 4 times, with the majority of it in France. The above-ground structure houses ancillary equipment such as compressors, ventilation equipment, control electronics, and refrigeration plants. The data generated by the LHC and LHC-related simulations was estimated to be around 15 petabytes each year. The computing grid was constructed as a component of the LHC to handle the vast amounts of data generated by its collisions. It is a collaborative multinational project that comprises of grid-based computer network architecture. The Large Hadron Collider's construction segment cost approximately 7.5 billion euros. It is one of the costliest scientific experiments ever built. Its construction was approved in 1995 with a budget of $2.6 billion. Plus an additional $210 million for trials. The LHC's initial testing was delayed for 14 months after it became operational on September 10, 2008 due to a magnet quench incident that caused substantial damage to more than 50 superconducting magnets, their mountings, and the vacuum pipe. The LHC smashed 2 opposing particle beams of protons up to 4 tera-electron volts or lead nuclei during its initial run from 2010 to 2013. The Higgs boson, various composite particles including the Botonium state, and the first generation of quark-gluon plasma were discovered during the first run of the LHC. The Large Hadron Collider's initial objective was to examine the likely presence of the Higgs boson, a crucial part of the standard model of physics that was predicted by theory but hadn't been detected previously due to its large mass and elusive nature. If the standard model was right, CERN physicists predicted that the LHC would produce many Higgs bosons every minute. This would allow physicists to finally confirm or reject the Higgs boson's existence. Aside from that, the Large Hadron Collider enabled researchers to look for supersymmetric particles and other hypothetical particles. Following the initial testing in 2008, the first operational run lasted from 2009 to 2013, followed by a lengthy shutdown for modifications that lasted until 2015. The second operating run was from 2015 and 2018, followed by another protracted stoppage until 2022. The LHC reopened in April 2022 with a maximum beam energy of 6.8 TeV. This round is projected to last until 2026. On July 7th, scientists were perplexed when a crack emerged in the Earth's magnetic field during the third run of the Large Hadron Collider. This inexplicable crack didn't happen in a flash of lightning, and it wasn't fleeting. In fact, the split in the Earth's magnetic field lasted 14 hours. The powerful solar winds were able to rush through the opening, causing massive geomagnetic storms and produce some really captivating aurora. The geomagnetic storm caused by this crack produced an aurora so spectacular that we couldn't take our gaze away from it. But how did this crack appear? As it turns out, this breach in the magnetic field was caused by a rare phenomenon known as a rotating interaction region from the Sun, or CIR. These CIRs are actually large-scale plasma structures that form in the heliosphere's low and intermediate latitudes when fast-moving and slow-moving streams of solar wind collide. The heliosphere is the area that surrounds the Sun and contains the solar magnetic field and solar winds. The co-rotating interaction regions, such as coronal mass ejections or CMEs, are propelled out from the Sun towards the Earth. These can contain shock waves in compressed magnetic fields, resulting in turbulent space weather, which we generally see as a gorgeous aurorae. This one struck the Earth's magnet in the early hours of July 7th, causing a long-lasting G1 class geomagnetic storm. A coronal mass ejection was embedded in the solar wind ahead of the co-rotating interaction region, according to National Oceanic and Atmospheric Administration (NOOA) experts. Should we be worried about this crack? According to experts, there is nothing to be concerned about because cracks in the Earth's magnetic field are rather common. This magnetic field works as a shield, shielding us from the Sun's solar storms. The various fissures in the field are thought to open and reopen rather fast, but these recent cracks have demonstrated that they can remain open for several hours at a time. We discovered that our magnetic shield is drafty, like a house with a window stuck open during a storm, said Harold Frey, lead author of a study on this discovery back in 2003. The house deflects most of the storm, but the couch is ruined. Similarly, our magnetic shield takes the brunt of space storms, but some energy slips through its cracks, sometimes enough to cause problems with satellites, radio communication, and power systems. Fortunately, there were no radio blackouts or power outages caused by this crack in the magnetic field. Residents of Canada and the United States, on the other hand, were treated to some mind-blowing northern lights. Scientists have also discovered that the Sun is approaching its most active period in the solar cycle, and that it is already exceptionally active much earlier than expected. This implies that your chances of seeing an aurora, which are now good, will only rise over the following 3 years. This breach in the Earth's magnetic field isn't the only thing discovered recently by the Large Hadron Collider. Multiple analyses based on the massive data set acquired in 2016 were presented to the public in July 2017. The Higgs boson's properties were explored in greater depth, and the precision of several other discoveries was enhanced. Since March 2021, the LHC collision experiments have discovered around 59 new hadrons in data acquired from the collider's first 2 runs. On July 5, 2022, it was revealed that a new sort of pentaquark composed of a charm quark, a charm antiquark, an up, a down, and a strange quark was discovered while studying the decays of charged B mesons. CERN, on the other hand, is also home to a number of non-LHC dark matter experiments, including CAST, which searches for hypothetical particles known as axions, Na64, which collides electron beams with atomic nuclei, and AMS, which searches for cosmic rays from the International Space Station. Dark matter is a hypothesized type of matter that is thought to account for a large portion of the universe. It is dubbed dark because it does not emit, absorb, or reflect light, and hence cannot be observed directly with telescope or other electromagnetic radiation detecting tools. Its presence, however, may be inferred from its gravitational effects on visible matter, such as stars from galaxies. Scientists estimate that dark matter accounts for around 85% of the mass in the universe, and that its existence is required to explain a number of known phenomena such as galaxies' rotating speeds and the distribution of matter on a cosmic scale. An international research team recently succeeded in dramatically narrowing the scope for the presence of dark matter thanks to a precise experiment conducted at the Albert Einstein Center for Fundamental Physics, AEC, at the University of Bern in partnership with CERN. The AEC is one of the leading international research organizations in the field of particle physics, with over 100 members. The team's findings, led by Bern, were recently published in the prestigious journal Physical Review Letters. What dark matter is actually made of is still completely unclear, says Ivo Schulthus, a PhD student at the AEC and the study's principal author. What is certain is that it is not composed of the same particles that comprise the stars, planet Earth, or us humans. Increasingly sensitive tests and methodologies are being deployed around the world to seek for suspected dark matter particles, so far without results. Certain hypothetical fundamental particles known as axions are a good candidate category for dark matter particles. One significant advantage of these extremely light particles is that they could explain other crucial phenomena in particle physics that are currently unknown. Thanks to many years of expertise, our team has succeeded in designing and building an extremely sensitive measurement apparatus, the Beam EDM experiment, explains Florian Piegza, Professor for Low Energy and Precision Physics at the AEC, who was awarded one of the prestigious ERC starting grants from the European Research Council in 2016 for his research with neutrons. If the elusive axions exist, they should leave a distinctive signature in the measurement apparatus. The measurements, made in collaboration with French researchers at the European Research Neutron Source at the Institut Laue-Langevin and CERN, enabled the experimental exclusion of a previously unknown parameter space of axions. It was also demonstrated that it was possible to search for hypothetical axions that were more than 1,000 times heavier than was previously possible with earlier tests. Let us know what you think of CERN's new discoveries in the comments below.